I'm Marty Alpert. I'm CEO of a small think tank company, Universal Empowering Technologies, and we've been working on issues related to quantum mechanics and how they could affect different systems in a practical way. I'm going to talk about the effect of changes in the number of superposition states at reset observation on system energy. My goal is to determine the effect of changes in the number of states on energy during the measurement process. I am proposing a different way for energy to change without a wave transfer of energy, and this is based on changes in the number of superposition states. And I'm proposing that the changes of the states occur instantaneously at the observed, which is slits in our systems, when the observer is either reset or makes an observation. I will discuss the justification for making these as well as the consequences for quantum mechanics. I am defining a state differently than is conventional in physics. A state is each discrete interaction in a system that can result in an observable. Based on this, I am proposing three independent assumptions. The first one is that changes in the number of superposition states result in an energy change. There's a recent experiment that showed a power increase for quantum heat engines that are greater than classical heat engines, which would apply to this assumption. The second assumption is that changes in the number of superposition states at the observed, or slits in our systems, occur when the observer is either reset or makes an observation. My third assumption is that the change in the number of states at the observed, or slits in our system, at reset or observation of the observer occurs instantaneously. And this could be a physical basis of the Copenhagen interpretation of quantum mechanics, since there would be no in-between states. States exist in space. Value or meaningful information is communicated by waves in time at less than or equal to the speed of light. I'm going to discuss the justification for these assumptions and the consequences for quantum mechanics. Part of the justification is based on information theory, and this is based on computer gates, primarily an AND gate, and the analogy to quantum mechanics. For an AND gate, energy is used to reset memory, not in the calculation. For slits, energy is used to reset the observer, not in the observation. When we have an irreversible system in an AND gate or in a particle slit system, interference results. And this is where the number of inputs is greater than the number of outputs. The inputs are in a superposition state, and information is lost. We cannot determine the inputs from the outputs. Energy is required to reset the observer or add memory. When energy is added to reset the observer or add memory, we end up with a reversible situation that has no interference. Superposition is eliminated, the number of inputs equals the number of outputs, and information is conserved because we can determine the number of inputs from the outputs, and there's no energy change in the environment. The inputs again go in a superposition state after the output is measured or the calculation is performed. I'm going to discuss the consequences of the definition we use for states. That is, a state is each discrete interaction in a system that can result in an observable. Any possible interaction between the source and slits, in our definition, is a state. And states can have particle characteristics which are distinguishable, and they can have wave characteristics that are indistinguishable, and these are a result of superposition states existing. Distinguishable states that have the particle characteristics are when the number of inputs equals the number of outputs, and this means that the number of slits equals the number of observers. And for double slit systems, the number of observers are the final detector screen and an observer of the slits. We have complete information, they are commuting, so that the observations are independent, and the order of observation does not make a difference. The number of states is a constant and is equal to the number of slits. What's important for us is there's no change in the number of states with added observers. When we have an indistinguishable system, we have wave characteristics. The number of slits are greater than the number of observers, We have missing information, so the inputs are in a superposition state. So these are binary, non-commuting, and the order of observation makes a difference. What's important for us is that the number of states varies with the number of observers. Now we can apply this to multi-slit systems as well, not just to double slits. So adding observers, or reset, decreases the number of possible interactions, our assumption 2. In the observed instantaneously, our assumption 3. So energy changes at the observed, our assumption 1. If the number of states, not the value, is significant, quantum mechanics can be related to statistical mechanics in physical systems. Both deal with a number of physical microstate possibilities that result in macroscopic physical observations. We are assuming that the energy change is at the level of a bit energy change. The discrete increments may be at something that is different than this, and we can determine this from experiment. What's significant is that one observer can instantaneously change a very large number of superposition states at the observed. If we take n equal sized discrete slits, the maximum number of change would be n times n minus 1 if we add enough observers. The number of possibilities is equivalent to the number of terms in the probability expression in multi-slit systems. For n slits with r observers, the number of terms is equal to the total shown here. I'm going to propose 2 experiments. The first is to look at observer reset and observation effect on the observed. What I want to do is monitor the energy changes in the observed, or box 1 here, and the observer, box 2, independently throughout the entire measurement process. I want to point out that there's subtle differences between the classic double-slit system and the interferometer model that is frequently used to test it. There are energy changes from the equilibrium state in box 1, our assumption 1. When we have reset, collapse of the wave function in box 2, we have a decrease in the number of superposition states in box 1, which will result in an increase in energy at the observed, again in box 1. At the observation of box 2, we have an increase in the number of superposition states and a decrease in energy. These changes are reciprocal, so we're expecting no net change in the number of superposition states. This is not dependent on the value or meaningful information, which is determination of the path information. And we can use this experiment to determine if energy changes occur at the observed, or box 2. The next experiment is used to determine if the changes are instantaneous. Adding or removing a slit from a multi-slit system occurs in time, but changes in the number of states in the system occurs instantaneously, and this has physical results. A good model of this is entanglement, where quantum information that we're defining as the number of states and gives us the amount of information in a system changes instantaneously. The value or meaning information is communicated by waves between the observed and the observer at the speed of light or less. The experiment we're proposing is to reset the observer and then move it away from the observed so that the signal distance traveled between the observer and the observed at reset is less than the signal distance travels between the observed and the observer after reset. There are 4 possible relationships between the signal transfer between the observed to the observer. Our interest, though, is in the 4th one, where the observer reset instantaneously changes the number of states at the observed. And this becomes an entanglement type process, and we would expect no interference. So this is not dependent on the time relationship between the source transit to the screen observer because it's instantaneous. We see this in delayed choice type experiments, where the reset of the observer has the ability to determine path information immediately before final screen observation results in no interference and has a space-like effect. Based on the instantaneous energy change, our assumption 3. Due to a change in the number of states at the observed, our assumption 1. As a result of the observer reset and observation, our assumption 2 does not explain quantum mechanics, but could provide additional insights. into the Zeno and anti-Zeno effect. It also has implications for a modified uncertainty that includes discrete states of the observer and the observed. It has implications for how wave-particle duality is related to what energy and mass are. And it has implications for dark matter and energy as well, because if the instantaneous changes occur in the lab, they would also occur at celestial distances, and they would be a function of the number of resets to the number of observations, and we just showed how this could be related to delayed choice experiments. I'd be very interested in any feedback that anyone would like to provide, so please contact me or leave a comment below. Thank you for listening.